Wow! Hey, Trip. How's it going? Look at the academic calendar. Oh yeah? What do you do? What's your research in? Trip? Oh, okay. That sounds fancy. Good luck with that. Ugh. All right. Now let's get class going here. Well, hold on. Class even here? Not. You have to wait. Okay. Hey, Femvox, how's it going? Ah. Hmm. Let's see if the color thing works this time. Let's do the prime numbers. Prime. Let's see what the prime numbers look like. Changed. Awesome. The prime numbers look like. Okay, 9:31. Class. You gotta be here. Okay, you must be here, hopefully. Maybe. Alright, we're in the thick of it. So we're getting into more sort of the heart of Galois theory now. We will be stating, we will be on the verge of proving the Galois correspondence definitely by early next week. So the reading is chapter 11. I think I'll get through like half of it today and then half of it Friday. Okay. So today's class is about the first part is kind of a review of some facts we already know. I just want to put them forward in front of us. And then there's a definition, a new sort of construction or useful concept. And that's the concept of normal closure. You don't have a normal extension? No problem. You can upgrade it. That's the point of normal closure. And you can do it in a kind of minimalistic, unique way. All right. And then I want to just talk about normality from a slightly different perspective than what its original definition says. Okay, that's the plan, and let's begin. All right. Okay, number one. I just want to put in one place various extension facts that I've been calling, or upgrading a particular homomorphism to an automorphism of a larger field. Those kinds of statements. All right, so let's fix some language. Suppose we have the following situation. We have a field, and we're sort of working inside of an ambient huge field. See? You have a field, and you then have two other fields that contain it. That's a very common situation in Galois theory. All right, we're going to just use some language here. A K homomorphism or K monomorphism, whatever, same thing. Is just a homomorphism from M to L which, when restricted to K, does the identity. Doesn't do anything. Okay? Doesn't do anything to the subfield K. And that's what the prefix K will mean, sort of universally throughout the class, or throughout most of these subjects, algebraic subjects. When they put the K out in front, it means a thing that preserves this K, that puts identity on the pointwise fixes this object. That's a common language scheme that you'll see. All right. So, for example, here's an example of a K automorphism. K could be this field, and M might be this field. 5th root of 7 and I. And L might be this field. Zeta times 5th root of 7, I, where zeta is a primitive 5th root of unity, say. Cosine 2 pi over 5 plus I sine 2 pi over 5, for example. Or any non-trivial whatever. Okay, so these are two fields that both contain K, and here's a K automorphism. Here's a K homomorphism of M into L. It's defined as follows. Now, why is this a homomorphism? By extension lemmas. It's by something I wrote a note about in your under notes, by that kind of fact. Okay, so it's what it does to these generators is it sends this thing to that thing, and it sends I to itself. And then that's not enough to know what it does to the whole field. Then you say, extend this in the natural way to a homomorphism on the fields. Why does it extend? I read one of the notes that I once wrote you. Okay, this and extend naturally. Yeah, that's an example. The point is, say minimal polynomial over Q adjoint I. Exactly. Procrastination. These numbers are partners over Q adjoint I. These two numbers. They are what will be eventually called Galois conjugate numbers. They are conjugate. Awesome. Okay, just so that you see weird examples. There's a unnecessarily complicated example of a K homomorphism. Similarly, K automorphism is when you're mapping into yourself. So the word auto means self. So you can just language we're getting under our so that we can say things faster. All right, so now I'm going to show you all the extension type, the most useful extension type statements that we've already actually seen all the proofs of. So I won't really go into the proofs too much. So here's the extension statements that are most useful and are used all the time when you want to assert that there's some element of a Galois group that has certain effect. Constructing automorphisms with desired effect. That's the theme of these extension type statements. Okay, suppose you have a normal and finite extension. All right. Oh, and now suppose that M is any intermediate field. Then every K homomorphism from M back into L extends to a K automorphism of the large field L. You can achieve, no matter how you do some field homomorphism from M into L, you can upgrade it to an automorphism of L within itself. Okay, so normality, you want to, by the way, the theme here is that normal extensions are in some sense, and the sense is built out of the facts that we're about to develop, normal extensions are in some sense kind of self-contained. They're kind of complete in a sense. Okay, algebraically self-contained from a certain point of view. Right, so you can upgrade a field map from M into L to an automorphism of L. That, in other words, there's an automorphism of L that when you restrict to its effect on M is this tau map. Tau extends to an automorphism. All right, why is this true? I'll just say briefly why. Because it's a fact we've already seen. It's a fact from chapter 9. Normal extensions is a splitting field. Normal and finite is just actually, you're looking at a splitting field. And this claim is a claim from chapter 9 about splitting fields, actually. Same exact one. I called it the naturalness of a splitting field, or the uniqueness of splitting field. Maybe this, I'll just draw a diagram that might jog your memory. It's something like this. I'll put M's in place of. If you have this, then there exists isomorphism on the splitting fields. Okay? I'm just drawing a diagram to jog your memory of the splitting field fact, but that's all that this is reminding you of. With M being the small field in this in that last statement. Okay? So visitations of the middle field into the large field L are all actually restrictions of automorphisms of the large field. That's powerful. That's good to know. Those kinds of things are very good to know. Okay? As a corollary, as a special case of this, suppose you have the same setting. And now suppose you take any number in L. Pick any. Now look at its minimal polynomial and choose any one of the roots where alpha will be one of them. So meaning, suppose beta is any root of alpha's minimal polynomial, which I'll write as m sub alpha. And I'll let you always deduce the meaning of that. Okay? Then there exists an automorphism, a K automorphism of L, which sends alpha to beta. Notice there are no uniqueness statements here. There is no uniqueness claim about this extension to as an automorphism of the ambient field. No uniqueness, and that's very important. Okay, all right. And there exists a K automorphism sigma such that sigma of alpha is beta. Why is this a special case of the last one? Why? Because you let M be this field, K adjoin alpha. Now, since L is normal, right? It's a comment. Since L is normal, this beta, this other root, is still in L. It could be somewhere else if L wasn't a normal extension. So beta is still in L. And the map tau is the map that's the isomorphism between K adjoin one root and K adjoin any other root. Those extensions are abstractly isomorphic, as we've gone over many times now. There exists an isomorphism that fixes K from K adjoin alpha to K adjoin beta. It just sends alpha to beta. That's what it does. And this is just a subfield of L still. And so you apply the previous extension statement to this map. Okay? And that's why you get the claim that there's a field automorphism of the large field fixing the small field that sends alpha to beta. All right? So in other words, in a normal extension, when you take an element, you get all of its partner numbers, which are the other roots of the same minimal polynomial. there exists. Yeah, there exists. Okay? In terms of procrastinitation's viewpoint. Now, in a normal extension, you can always guarantee that there is some automorphism that sends one element to any one of the other sister elements. In other words, the Galois group, the group of automorphisms of L over K, acts transitively on the roots of irreducible polynomials if the roots are in the field. So I'm going to say that as a slogan. If L over K is normal, then this Galois group acts transitively. Okay? Just a slogan. For normal extensions, the Galois group acts transitively on these little packets that procrastination likes to think in terms of, and that a normal extension does not interrupt. Awesome. So that's the first thing I want to talk about. These extension type statements that give you confidence in saying that there is an automorphism of a normal extension which has some desired effect. Finite normal extension. Awesome. All right, let's continue. What does transitively mean here? Transitive, so a group acting on a set acts transitively if for any two elements of the set, there's some element in the group that sends element number 1 to element number 2, for any two. There's one orbit under the group action. That's what transitive group action means. Okay? So we're starting to see last semester's language come back. Of course, I mean, it's all one mathematics. All right, so 2, concept of normal closure. Okay, when normal extensions are just better than arbitrary extensions. They're more, you have these kinds of extension statements for them. You know, the Galois group acts transitively on the roots. It's just, the Galois correspondence starts to be true as long as you also have a separable extension, which will not be an issue for us. So, when you don't have a normal extension, is there a way to upgrade? I'm going to write a sentence here. There is a way to upgrade any extension, any finite extension, any finite extension to a normal extension. Okay, it's going to be bigger than L, a bigger one, but at least it's normal. How do you do it? It's actually a massive intersection. All right, so how? Okay. Because you know why? It's probably too early. And also, I have a feeling that it's a little bit too not calculus with like pictures and stuff. Yeah. Okay. Okay, so how? Easy. What you do is it's a classic subgroup generated by or span of a set of elements in a vector space or whatever. It's a smallest field that's normal that contains L. Normal over K and contains L. So here's how you set it up. You let like script n, say, be the set of all fields. Let's call them F. Contained in C, that's our ambient home that we've just fixed in this first part of the class. All fields F, such that F contains L, say, and F over K is normal. Now, I want to point out that this is non-empty. And there's actually a cheating way of seeing this. Hey, Arbitrary, how's it going? There's a, yes, procrastination. There's a cheating. Q bar. Normal doesn't imply finite. Finiteness, you had to put that extra assumption. Procrastination, you like this? Do you like this answer? Yeah. Yeah. Unsatisfactory, but it's great. All right? There's one field. It's always going to work. Yeah. Normal extensions are algebraic, and they have this, if you have a root in me, you have all your roots in me condition. If you're irreducible. Irreducible, have a root in me, you have all your roots in me. Irreducible over the field K. Okay, there you go. Good question. Wow, wonderful questions. We'll address that right after this. Procrastination. We'll address it right afterwards. Okay, so how do you construct a normal closure? Normal closure is the following. It is the field N, which is the intersection of all the fields in this set of fields. That's the normal closure. Okay? Now, the claim here is, okay, this is a field. Claim. So what's the claim here? This is a field. That is silly. I don't even want to. You do that. This is a field. 2. This contains L. Again, very dumb. This is just, each of these contains L. F, all the F's contain L. Okay, so this is a bigger field than L. Okay. 3. It is normal over K. This is practice for unraveling the definition of normality. If you've got an irreducible polynomial over K, and it has one root in me, it's got all the roots in me. That's all you got to prove. But that's true about each of the F's, because they're each normal over K. So this is also obvious. And this is the smallest field that contains L and is normal over K. Because look, it's the intersection of all of the possible ones. It's contained in all the others. So this is the smallest upgrade. To a normal extension. It's called the normal closure. Okay, procrastination asks, if you start with a finite extension L over K, is the normal closure also a finite extension? Good question. Yes, let's prove this. L over K is finite. Means L is obtained by adjoining a finite list of algebraic numbers. Okay? I assume you understand what the alphas mean. Just a bunch of generators, finitely many. Okay, write that. And now, for each one of these alpha i's, write down the minimal polynomial. And now, write down the following splitting field. Oh, here's the polynomial. F of x is the product. Write the following splitting field. This field extension. Splitting field. Now, what do you know about splitting fields? Here's a quiz. What do you know about splitting fields? They are normies. Exactly. First of all, it's, of course, they're finite because, obviously, you're adjoining all the roots of this polynomial f. But there's finitely many. So there you go. They're normies. This is a normie. But hold on. It contains L. Because L was adjoining some of the roots, namely alpha 1 up to alpha n. And sigma is adjoining all the roots of this polynomial. So sigma f is in this fancy n set. And so the normal closure is contained in here. And of course contains k. But then this extension has to be finite. Because sigma over k is finite. Okay? You sandwiched it. Awesome. So the normal closure of a finite extension is another finite extension that's bigger, possibly. And it's the smallest among normal extensions, upgrades. Great. Okay, so let's move on. Let me show you an example real fast. Obviously, if you're already a normal extension, your normal closure is yourself. That's stupid. This is dumb. Yeah, very dumb. Okay, but flusha. How's it going? Okay, but here's one. The normal closure is this extension. Oh wow, not prof. Why'd you raid? Jeez, amazing. All right. Welcome. We're doing some normal close. We're closing up. We're doing normal closing. Okay, this is the normal closure. All right. Now, why don't you try to understand why this is the normal? This is a normal extension that contains the first field L. And it's a splitting field, obviously. But is it the smallest normal extension? It's obvious. I mean, I'm just saying, button all the, dot all the I's to make the claim exactly perfect. All right? Thanks, not prof. I hope you're having a good day too. All right, so now I'm going to talk about another way of thinking or witnessing normality. And then, man, after this, you guys will be world experts at the concept of being a normal extension. You will appreciate it from many points of view. So, witnessing normality in another way. Okay? Exactly, procrastination. Exactly. Okay, that's definitely one way to do it. You can also do it by the definition of normal. But anyway. Oh, hi TK agent. How's it? Okay, so here's a perspective. And I've written about this perspective in the notes, one of the notes I wrote a while back. Okay? Suppose you have a finite extension. Consider the following set. This is a thing to think about. It's a set to think about sometimes. Consider the set, I'll call it E L over K. It's the set of K homomorphisms from L into the complex numbers, or Q bar. They're the same because we're looking at a finite extension. So we're in algebraic world. It's the set of K homomorphisms of L into C, or Q bar. Same thing because L over K is finite. So all numbers as outputs will be algebraic numbers. K homomorphism. This is a K homomorphism. E is for embeddings. Ways of embedding this extension, L over K, into complex numbers, which keep like the subfield K as like anchor. All right, just kind of have this kind of weird picture. Ways of manifesting the larger field as a subfield of the ambient world. Okay, that's a set. All right, and lots of these definitions and constructions and ideas in field theory can be sort of thought of in terms of basic facts about these sets, the sets of embeddings of a given large field into the complex numbers, the set of manifestations of this extension inside of the ambient world that we're looking at. Okay, so here's what normality means now. Cool interpretation. It's like a grown-up interpretation. It's a theorem, okay? Or it's theorem 11.9, but my way of thinking about theorem 11.9. Okay. L over K is normal if and only if for any element in the embedding set, for any way of embedding L as over K as a field extension in complex numbers, the image is L again. What happened? This became a parabola or hyperbola. Really, the emphasis is that the image of this embedding is back inside L. That's the emphasis. You see, this is getting at a certain internally self-containedness of a normal extension. That if you abstractly try to manifest this extension in another way inside the complex numbers, no, in fact, you were just scrambling the same extension. It didn't become a different set. There was no other field extension that was abstractly the same as yours. So let me show you an example where this is clearly false. So look, you've got this, but you also got this one. This is my L, this is my K. Notice that there is a way of mapping L over K, a K homomorphism, from left field to right field. There is this tau. This tau is an element in here. There is a tau like that. But notice that this image, this is tau L, is not back inside of L again. That is, in fact, how you can think of normality for an arbitrary extension. That there's no way of mapping this extension in a clever way that escapes the field itself. Every such way of mapping just stays within the field. It's a self-containment property that normality enjoys. All right, so this is a cool if and only if statement. Yes, and it's in line with not disturbing orbits of certain things, or like not disturbing packets. That's another way of that normality is kind of an inclusive property. Okay, so let's start thinking about the proofs of this simple. It's not that hard of a if and only if statement. Okay, at least not in my mind right now. Okay. So let's prove one direction. If you're normal, then you can't have inventive re-embeddings of the large field as an extension over the small field. You can't have inventive re-embeddings. They have to all land back inside your field. Let's prove that. I'm anticipating it's easier. Okay, suppose L over K finite and normal. Okay, and choose a K homomorphism. So this is an element in the ways of embedding L as a subfield of C intermediate to K or whatever. Okay, now look, pick any alpha inside of this, in this L. Okay, now alpha is an algebraic number because L over K is finite. So you can talk about its minimal polynomial. It's algebraic over K. So you can talk about its minimal polynomial. Okay, let's call it M. Oh, let's just call it M. Not too many alphas. M of X. Okay, claim. Tau of alpha has to also be a root of M of X. This is we've seen this sort of thing so many times now. It's the same exact proof. Tau of alpha must also be a root of M. Why? Because tau is a K homomorphism of fields, not a random map, but respects addition, product, and it fixes elements of K. And so that's just, I'm just going to write that. Tau of, so, okay, let me write it out. Tau of m of alpha, this expression is the same as m of tau of alpha. But on the other hand, this is 0. And so tau of alpha is a root again. Okay, but then you're done because L over K is normal. So tau of alpha is again inside of L by normality. Just a definition. And so I took any element in L, I looked, where did it go? It went back into L. And so I get this containment, the emphasis one. But hold on. Tau is actually, yes, it's a field homomorphism, but it's also a linear transformation of K vector spaces. Is a K linear map between two vector spaces. And these two vector spaces, they're the same vector space. And they're finite dimensional. They're the same vector space. They're both L. Same dimension. Meaning this degree. Same dimension, finite. And it's injective. So its kernel is 0. Rank, nullity, all that's true. Arbitrary field. It just comes from row reduction. And so injective map between two vector spaces of the same dimension has to be an isomorphism. And so, indeed, tau of L equals L. Okay? So let me say slightly more refined. If L over K is normal, every way of manifesting L back into the complex numbers as an extension of K is actually just a field automorphism. You're just doing field automorphisms of L over K. Galois group. All right? And so the other direction is slightly more entertaining, though not very much actually. All right, so the other direction, it will use extension lemma thing, I think. Let's just leave the other direction for next time, but let me set it up. Suppose for any tau, the image of tau was just L. You want to show that L over K is normal. Okay, let me get you to the final sentence. Let me get you really close to it. And then see if you can use an extension lemma that we've already seen before to get it. To clinch the thing. Remember, L over K is a finite extension, by the way. Okay, suppose you got this. Such that every way of embedding just sends the set back into itself. Okay. Suppose alpha is a root of an irreducible polynomial and now pick any other root. We want to show beta is back in L. And all we have to work with is that whenever you embed L back into C, embed L in C, and while fixing K, the image of that embedding is back inside of L again. That's what we know, and this is what we want to show. So now, between now and Friday, I want you to try to like piece together the extension type statements that we've seen now many times, and see if you can get this to the end of this proof. I'll do it really fast at the beginning of Friday because it's 1 or 2 lines for me. Okay, but I want you to practice trying to pull these levers. Do I drink coffee? Yes, I'm drinking coffee right now. Okay, so let me, maybe if there's any questions or anything you can ask now. Class is over because it's 10:18. Let's do our traditional thing. Procrastination. Great student. Not actually a student, but really asking good questions. All my students, all my actual students, all 3. Thanks for showing up, maybe, probably. Yeah, we're getting more subtle into field theory. This is getting more subtle, so make sure you're not overconfident. In my experience, that's a problem. With sugar and milk, or yeah, I'd say random. Sometimes with, sometimes without. Yeah, they do, Vixen. They do. They show up like every time. I'm pretty sure. And it takes away from the coffee. Procrastination, yeah. That's funny. All right, Crow is here. Vixen, of course. How you doing, Vixen? Arbitrary. Not prof. Hey, was there any news with Melko? Wasn't there going to be some kind of thing? Good news? What happened? I didn't catch it. Do you guys know? It's for math majors and graduate. It's for master's students and math majors. Yeah, exactly. Saipet shows up. RDL shows up. I think Itasuk shows up. Maybe it's the same person. All right. Well, there's 3. I don't know. Hey, MHZ, welcome. I saw you in chat. I just scroll up, and I just write down who's here. Trip. New person. All the people that followed. TK. Lusha. Okay, that's it. That's all. That's not. I act like it's like a lot, but it was just 2. The Twitch email is gonna be just so sad this time. You know? It's always like, oh, keep up the grind. Keep fighting the good fight. That's what the Twitch emails are these days. That's what Galois Theory does to a stream. All that, you know. Slumberg. Yes, exactly, Kappa. Lots of family members, like Slumberger here. Probably a family member. Probably a cousin or something. Thank you. Thanks for that pity follow. Yeah. Well, that happened. I didn't. That just happened. Procrastination. But procrastination, I have to be honest. I can handle larger teaching load if like the topics are somewhat close and simple. But this time, this is now pushing my brain. Like I have to actually think hard. Especially later today, intersection theory. But it's my bread and butter, so it's going to be very fun for me. But still, you know, you have to really prepare for those kinds of things. And then commutative algebra. Very hard to make that subject fun. But it's also a difficult subject. It's just, my brain is like just completely, I'm not prepared for this level of stretch in different directions. It could be much worse. It could be that like I'm teaching like some analysis or something, and then I should try that just for like, you know, you're supposed to do like crossword puzzles as you get older to like keep your brain active. I should try to do like 2 graduate courses in opposite sides and see what like, and do like a science experiment, you know, like social science or some psychology.
Yes, science!
And see what happens to me by the end of the semester. %, Vixen, 100%. It's objective fact at this point. No, not for us, Crow. Yours is gonna be online, Crow? We're most likely not. So no more classes online, probably. Though I'm teaching history of math and 2 Calc 3s because I'm overloading my teaching so that I don't teach in the spring. History of math. That could be good online. With this, you know, with this TV channel thing. That could be fun. But it's probably in person, and I can't draw pictures of Galois or whoever, you know, Euclid on the board. History of math. It's the first time I'm teaching a class that's not chalkboard. Like, I'm guessing I'm not going to be able to just write sentences about history on the board. So I'm going to have to use something. Well, procrastination, I'm pretty sure the advanced like intersection theory class seminar will continue until it just becomes too crazy. I don't know. So there will be special topics. There will be harder algebraic geometry still on here. Well, I'll still record. I'll have to get back to recording videos for graduate students. So that will continue, but probably not entire classes. Though I got really, really good reviews from the higher ups about what I did, the way I dealt with the COVID transition. So I don't have to hide this thing anymore. I don't have to hide. It's a they support it. But there's just not going to be that many online classes, people, in the fall. I anticipate. Yeah. I wonder if it's illegal to ask the history of math class, like we meet the first day in person and whatever, and say, "Hey, um, check out this channel, this TV channel. Would you want the lectures to be on this?" And then just tell everyone that we're actually meeting. It's just everyone just happens to be really, really bad student and stays at home, including the professor. It's just a train wreck of a class. Is that cheating? Is that illegal? It's probably illegal. There's something, this feels something off about that. Yeah. Really, Crow? Oh, you pulled it off? Okay. Really, Vixen? Wow, I didn't. Oh, I don't understand that. Wow. But I don't understand everything about anything. Oh. Hmm. Arbitrary says, "You're always so precise when we talk about history of math. Like, quote, millions of years ago, ancient Greeks used square root of 2, dot, 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 unquote." Exactly. Could you imagine a history of math class? Just filled with just wrong things? That's what I plan to do. This is an async class, so we won't be meeting, and I just want to meet the first day to go over the syllabus. Wait, but it's an async class though, right? I mean, that's fine. Wait, that's Pro, that's how it's supposed to be. Asynchronous. Yeah, that's totally fine. I mean that I'm talking about a class that's supposed to be normal. And then I just say, hey, should we do this? Oh. Oh. Yeah, oh, yeah, she did exactly. Mm-hmm. I'm wondering if that's, yeah. I mean, you don't actually have to be very worried about these things, in my experience, if you're good at teaching. You just do what needs to be done to make the students feel like they learned something. Most places will let things slide if if you're on good terms. Um, you're a good departmental citizen. At least I hope. Oh yeah, actually, computer science. Yeah, yeah. My brother's doing computer science classes, and it's like asynchronous, and it seems really boring, like that way. Like it seems hard to be motivated internally if you're not like a very driven person. Yeah, yeah. That's what it seemed like when I saw it. It's hard. Yeah, you get very little interaction with the professor. Oh yeah, exactly. Exactly. I do. Vixen says I do mine asynchronous, and I still get. But Vixen, I think asynchronous will just give you lower evaluations because of what Crow and I are talking about. It's just something about it, like. Yeah. You might think it's like more convenient and stuff. Something about the engagement that makes students sour, like, more easily. Oh, okay, that's different, Vixen. Okay, well, that's different. I was trying to make you look better, but I guess. Yeah, that's true, Vixen. You can watch it at 10 times speed. However, when you do synchronous, yeah, they kind of have to be there, and you're supposed to like look at who's here and who's not. But we were never allowed to enforce attendance during the COVID thing. And so in effect, they could watch the video afterwards at 10 times speed and just sort of keep the video on while the class was meeting. Yeah. Not giving my students any ideas. Sync online, but lectures are recorded and emailed to us. Right. Slumburger is not a cousin. Oh wow, thank you, Slumburger. Wow, what a great person. They like what I'm doing. Slumburger, just scroll up the chat. We don't do compliments here. They're not. You know, we don't do compliments. It's one of the most toxic math communities around. So, you know, I'll let it slide this one time, but we don't do that. And you don't have to do compliments to make it onto the credits screen. You just have to say any garbage. Look, for example, in your aerial just followed, but that's because they want to be on this screen right here. So yeah, here it is. In your aerial, here you go. Probably another cousin. I have lots of cousins. Alright, there you go. You happy? Is that why you followed? There you go. You see that? You feel that? That dopamine? Right there in the cerebral cortex, right by the fusiform hypochondriac.
Yes, science.
Hypothalamus.
Yes, science.
Did I miss anyone? Fembox, I think I got you. Right. Okay. It's just you were, you know, you were there in the beginning and then you fell asleep and you came back or something. So it's not my fault. Okay. Okay. So now I need to switch my mind. The Aquabats doing science. If I open that right now, will I be like sued or something? I don't want to open it right now, but is it a bad video? Vixen? Oh, you just had to clear your name. Oh, being... I didn't know that being a cousin of mine was an insult. Slumber. I didn't realize that. Thanks. Clear my name. Ah, okay. I like that. Yeah. Okay, commutative algebra. Right. I'm doing something difficult right now. Primary decomposition. Need to think about it. How to make it understandable. Okay. Wait, so wait. Did people figure out the Melco news or no? Let me just scroll up. Oh, actually, he isn't check mark yet. But there's like several possibilities of the news, right? Vixen, is that? Kappa. Hey, wait. Did we get Kappa? Where's Kappa? Ah, we have such good moderators here. They don't do jack shit, but whatever. I mean, they're good. Is it true that news stands for Northeast, West, and South? I mean, I can give a whole lecture on news. I mean, I'm a professor, so I can lecture on anything. But you know, news is in my opinion, news is information about current events. This may be provided through different media, like word of mouth, printing, postal systems, broadcasting, electronic communication, or through the testimony of observers and witnesses to events. Now, common topics for news reports include war, government, politics, education, health, the environment, economy, business, fashion, and entertainment, as well as athletic events. Did I mention that? Quirky or unusual events, etc., etc. That's what news is. What does it stand for? Let me think about it. Now, it's said that the English word news developed in the 14th century, I believe it was, as a special use of the plural form of new. So, in other words, you're wrong. In Middle English, the equivalent word was niwes, like the French nouvelles. Okay, guys, I'm actually just reading Wikipedia. I gotta admit, I'm sorry. The myth that it was made after the first letters of the compass, north, east, west, south, is wrong. Crow. It actually addresses you specifically on the Wikipedia. Yeah. Wait, arbitrary. Is that the news? We shouldn't spread misinformation about Melco here. That would be a tragedy. Yeah, but it could be like astronaut. It could be his DC thing. It could be anything. Like, he's got so many things going. I mean, that guy. It's all those mob connections. But anyway, I'm glad the mob is pulling through for him. Whatever the news might be. Adjacent? Wait. Let me just hold on. Jason is a hero of Greek mythology who led the Argonauts and married Medea. yeah, I guess I hope Jason 3 is the 4th mission in US European series of satellite missions. Wait, Jasons are the semi-secret group that hangs out in San Diego for 3 months and pretends to talk about nuclear. Wait, what? Yeah, it's that secret. Wow, this is like insane. Wait, what? Is it in Wikipedia? Oh, is it the USA Defense Oriented Consulting Group? Vixen? Elite scientists. Oh, I can't see that, but I think I found it. Wow. Why am I not there? I mean, we do science here all the time.
Yes, science.
Like, do they need any advice on like Galois theory or like algebraic geometry? What do you... Oh, who is this asking? Crow. What do you mean, Crow? Do you do pure math? Have you never gone to my website? Crow, in all this time? Of course I do pure math. And it's not in my free time. That's one of my main job requirements. But it's not a requirement because it doesn't feel like one because it's fun. But yeah, I'm an algebraic geometer. Well, that just means Crow. What that means is it's pure math. And free time, sure. It's part of my that's what I consider myself primarily as. Yeah. So what do they call you? They? They. Yeah. That's what but you know, I don't think people really emphasize the pure. They don't. It's a very cringe thing, this pure unpure thing. Okay, it's not unpure, but applied. I think only the applied mathematicians put the applied as a adjective. Because they kind of want to specify that, like, or in like job, when you're like looking for a tenure track job or something, the job will say like, might specify like pure and applied if the department has a divide, has like, is hybrid. But you don't really call yourself, just say you're a mathematician. Do the applied people look down on the other guys? I think it's actually the other way in my experience, to be completely honest. I think it's the other way. Exactly. Yeah. Crow, the idea being that if you're doing pure math, it means that you're lifting more intellectually difficult stuff. And now this might actually have something to it, this part. That the rules of the game are way more strict because you're proving theorems which are, you know, Let me tell you about inductive versus deductive logic. Reasoning. Inductive reasoning, Crow, is a method of reasoning in which the premises are viewed as supplying some evidence. Wait. No, wrong one. Deductive. Okay, whatever. It's a different rules of the game. It's some philosophy stuff. It's above your head, Crow. Just listen. And that difference causes this superiority complex. Okay? However, the ultimate point is that if you went back like 100 years ago, maybe a little bit more, maybe 200. Stay tuned for my history of math class where I'll have all this down perfectly, of course. If you go back far enough, this distinction didn't exist because mathematics was so intertwined with the need for it, why it emerged, which was coming from the world. So there was no real like thing like that. But it's still true that one type of person is motivated by some concrete thing, then tries to model it using a mathematical scheme. But I would say that I would just wonder how the referee process goes in that area. I'm just saying. What is it like? Like, what counts as a publication result? Is it like, look, empirically this thing seems to work out. Looks like the model is pretty good. Look, we did some statistics and it agreed with this to this p-value. Not bad. Is that, if that is, then completely different intellectual game. But the modern math is far beyond what technologies need. Exactly. Yeah. So now it's sort of separated. Arbitrary. Yes. Now I would say it's definitely a separated thing. Meaning that people who go into pure math are not motivated by any real problem, really. I mean, there might be real problems that gave rise to a math problem, which now math has become an industry or a chunk of mathematics, like Navier-Stokes equations, those kind. You'll find a lot of it in analysis, this kind of initial seed. But they're not actually trying to understand like a particular fluid or something. They really are motivated by the differential equations, period. Because they find them internally fascinating. Okay, so you're not really like thinking about this particular fluid or that. You might vaguely, but it's not like you're driving force anymore, typically. In the more algebraic side, there are obviously applications of algebraic mathematics. Like the classic one is anything that's a problem that's hard one way and easy the other way. And so those kinds of situations are useful for setting up security schemes or transaction communication. But that's very rarely the motivation of an algebraic geometer, for example. Personally, I come from a tradition where there's always a formalization, however small it is, of a result and the experiment. In silico. Man, Kappa, the vocabulary is just beyond me. Okay. Always to exemplify / show. Now, which one? Which one do you want to use? Exemplify or show? Maybe it's kinda. Suddenly it's kinda. So you had exemplify earlier, formalization. You had the word in silico. God, what is this? Who is your target audience here, Kappa? Me or like? Sometimes people are vague and dubious in their claims too. That exists. Yeah, exactly. They don't teach this stuff, man. Kappa, this is, we're NA education here. Hey, cyanide dinner. No, I think I don't recommend that, but welcome. Welcome. It's like multiple personalities live in one Kappa Klaus body. Exactly. Oh yeah, he's arguing for equal standing. Yeah, I don't think it's about equal. Yeah, I think it should be. I think it should be because it's understood that they're different games. It should just be understood that they're different games and not try to like make one fit into the other. At this point, they are different games. Different motivation, different it's just different rules of the game. In the physical sciences, applied and experimental triumphs over all. I'm not gonna touch that one, Vixen. As you know, there's some people on Twitch that are all about the string theory. Let's not talk about that. String theory. Not talk. Yeah, motivation and possibilities are way different. It's quite interesting. Actually, Kappa? Yeah, no. Do I have this superiority complex? Yes, I do. Because I'm on one side. That's why. But when I actually sit and force myself to think about it, I am actually jealous of the ability of a practical minded person to like quickly not get trapped by imprecisions, which don't really matter. And when you're a math person, you're kind of like always worried about like, well, is this exactly gonna work out? Is this how it works? Because you're worried about the proof structure, the gaps in reasoning, and so on. But I really like seeing when people just go problem solvey kind of, don't worry about this, let's focus on the main matter at hand. I kind of like that skill. And I very, very respect it. Respect it a lot. So, but that hurts my pride. So then I don't say it, and I just go back to being superior. Do you know Michio Kaku said when he looks at the sunset, he sees equations? Let me guess. He was on camera, and it was like a whole set, and it was like filled with money. in his pockets. Yeah. There's a book deal or something also in the works. I'm just gonna say it. These are not actually research scientists. The people, they're like, they're not actively in the game. They are entertainers. Not all of them, but some particular ones. Exactly. I think it's important for there to be people that try to express ideas in a way that's understandable to non-experts. I 100% think that's a good thing. But you don't have to like oversell either. And if you do, I think that you should make it clear that, or it should be known that there's a whole part of the world, active scientists, who do crazy awesome contributions without saying a word to the masses. They're kind of unknown. They're not on the learning channel or whatever, history channel. Yeah, so that's one thing I don't like to see very much. I cringe. That's one of the many things I cringe at. Kappa, that's what I mean. PDEs, but they're not working on PDEs because they're imagining, wow, I've got this river and it's moved. If they are, that thought isn't doing as much work as it's not. They are in that subject because they like PDEs, period. Absolutely. And their theorems are theorems. They're not empirical claims. Yeah. Oh, it's one of the most beautiful, deep parts of mathematics. A huge fuss about prime number. Oh, what significance do they have? Okay, here's a problem. So the significance is in more of the discrete side, right? The basic thing is that the basic observation is that every number is a product in a unique way of these prime numbers. They're kind of the atomic building blocks of arbitrary numbers. And it turns out that it's really, really computationally intensive to figure out the prime factors if you're given just the number. It's a real chore. And when things are a real chore, Cyanide, there's an opportunity to build a security apparatus, like a lock and key mechanism around that difficultiness. That is one of the, you're a practical minded person. That's one of the main sort of practical uses of prime numbers. Figuring out the atomic building blocks of a number just from the number is a real chore. And it's part of the essential part that makes cryptography systems, certain ones, work, meaning makes it difficult to unlock the lock. All right, that's just a practical answer for you. Now, I've heard some Michio Kaku type things. You want to hear a Michio Kaku type explanation? Right, never last. Yeah, that's a mathy answer for sure. I know what you mean. In fact, they are just the cyclic group, Z mod PZ. But yeah, there's also they also serve as a simplified setting. They simplify some headaches that happen in algebra when you have a composite number in front of you rather than a prime number. They're kind of a simplified setting, as Kappa is saying. That's also true. But I wouldn't say that these are physical like world. Like they're asking about the significance with the physical world, like calculus or algebra. So I don't know. Prime numbers are the fingerprints of the integers. Exactly. Good way of thinking about it too. No, but I've heard some stuff. Have you heard this one? There are some. This is gonna be Michio Kaku, okay? There's some beetles. Do you guys know what I'm talking about? Beetles? Cyanide, are you even there anymore? Whatever, maybe they left. There are some beetles. Cyanide. However, the difficulty of extracting the prime factors is not something that's just hard for humans. It's in a way you can qualify these things using mathematics. Like you can actually quantify difficulty in terms of mathematics. So like sure, it seems it's almost like flow of information, measurement of a flow of information one way rather than the other. One way it's easy, the other way there's lots of friction. Yeah. And also, by the way, algebra is like, what's the use of algebra? Algebra is useful for human beings to understand situations, Cyanide. I'm not sure why you think algebra is in nature, but not like arithmetic and prime numbers. Why do we do algebra? Why did it arise so late in human history if it's so natural? Algebra is a thinking device. It's all about human beings, meaning a human being's relation to the quantity world, the world of quantities. So if you include algebra, kind of hard to then say no, but prime numbers, factoring, fingerprints of natural numbers, I don't include that. But like the algebra isn't actually sort of the actual like X and Y and symbols and so on, and the expression of the relationships, like it's a way of understanding the actual thing, phenomenon. But it's just true. There is a difficulty in solving certain math problems. And this difficulty is universal. It'll be true for aliens. But knowing that is part of mathematics. For example, in this class, Galois theory. I can give you an example. In Galois theory, I think this is the polynomial. This polynomial, try to solve it. Find a number that solves this algebra problem. Okay, it turns out that there's no way to express any one of the roots of this degree 5 polynomial using these algebra operations. Divide. Nth roots. That's actually one of the conclusions of this Galois theory course. Now, that statement is like in the fabric of the cosmos. The basic concept of numbers is all that's being addressed. And when we say there's no way to express the roots of this equation using those symbols, it's true even for aliens. So it is actually fundamentally true at a fundamental level. Not about human beings and their inability to do certain things. And it's actually, to witness it, it's actually really convenient that this is a prime number. Because it sort of simplifies the analysis. And that's a reflection of Kappa's observation, that when asking questions about numbers, especially like integers and rational numbers, having prime numbers at certain spots helps simplify the potential possibilities that could have happened and could have been exploited in this situation. But yeah, the difficulty of expressing this is not something about human beings. It's like fundamental to the concept of, it goes just down to the concept of numbers, period. Yeah. Yes, but cyanide, the point is that this fact here is not an empirical fact. It is not a fact just for human beings, for their, when aliens come here and you write this down, you'll write, oh, you can't, this is a mysterious number. You can't express it using nth root symbols, plus, minus, times. They will agree with you because this is a universal fact. Like gravity, if you'd like. But it's a fact about numbers, quantities. Either you think that's a real thing or you don't. But I think at that point you should stop trying to divide whether a quantity or a number is a human invention or actually in the world. But I'll give you another one that's actually in science. If you can't express a number, then what's the use of that number? The use of that number is to tell you that the concept of number is not some easy thing. It's not what you initially thought it was, which is you just have to slap some square roots and you'll be able to solve any polynomial. No, you won't be able to solve every polynomial algebra problem by just using certain operations. You won't be able to. There is a fundamental difficulty in solving polynomial algebra problems, which are the first most basic algebra problems you would ever try to solve. There's a fundamental mathematical difficulty. But don't you guys find it strange that we can envision existence of such a thing, but can't see it or even visualize it? Yes, but we get used to it as mathematicians. This one chapter, it happened in the 1800s, actually is like it teaches us that lesson forever almost. It's a classic example of this kind of impossibility claim. We know it's there without having seen it. We know something is there in an indirect way. We know a phenomenon is there in an indirect way. And that's actually the allure, part of the allure of the subject. Yeah. But there's another one. Have you heard the one about like those beetles? Yeah, not prof, but isn't that dude like totally overblown? Like, for example, not prof. Have you ever been to a conference where like, oh, and now we use the lemma of this person, or have you ever heard the person being mentioned at any math conference? I'm curious. Like, I've literally never heard this person, like in any of my circles, which is substantial. It's not a small circle. I don't know how mainstream this person is. Not prof. Exactly. I think it's a YouTube personality situation. Yeah. The Beatles. Apparently there's some Beatles. I'm gonna mess this up. But you guys know about the Beatles? Okay. These Beatles, they lay eggs every some number of years. I forget how this goes. Okay. And then there's like another beetle that also lays eggs. Do they lay eggs? Do beetles lay eggs? Oh my god. Every some number of years. Sure, cyanide. Whatever makes it make sense to you. Either the bug or the beetles. Whatever. It's just as accurate as a story. Alright? And the Beatles figured out that if they choose prime number intervals of laying their eggs, the eggs don't compete with each other as much. As if you see it? You see? Because there's the least common multiple is bigger than it would have been if there was some possibility of a common factor. So yeah, the beetles evolved into prime number intervals between eggs to reduce competition. Yeah. Yeah. That's true. That's real. It's as real as gravity. Cyanide.
Yes, science.
See, look, Hang's mate knows about this, right? Hang's mate. Did I say it correctly about the Beatles? Isn't it something like that? There's something like that. Hey, pandemic, how's it going? Oh, okay, we've got new people? Probably. Yeah, probably. Exactly. Probably. Probably is good enough for me. All right. Pandemic is here. Hang's mate. All right. Cyanide. New friend. Cyanide, fact might be a generous term for some of the things I say. cyanide, especially if they're out of my expertise, which is everything basically is out of my expertise. So facts, I'm not sure if that's the right word, but I mean, it's nice to believe such a statement. It really feels good. Hang's mate in 1 is a chess player. Yeah. Wow. Thank you for letting us know that. Badster. Badster, thanks. Yeah. Okay, but now I need to learn. Yeah. Yeah. Little discoveries or fantasies. In my case, it's usually fantasies. But yeah, Beatles and prime numbers. Let me just Google that. Beatles and prime numbers. Yeah. Cicadas in their prime. The cicadas' love affair with prime numbers. The New Yorker. Wow. Was this written by Michio Kaku? No. Beatles. Wait, so what's going on? What's going on here? A cicada emerged. I saw that. Wait, a cicada emerged with 57 years once, and growth indeed stepped on. Exactly. Yeah, 13 and 17. Wow. Okay. All right, now I have to switch to commutative algebra, fancy stuff, and make sure I know what my message is going to be for my next lecture. And then at 6 p.m., hardcore intersection theory. Very, very mature audiences. That'll be fun. Very fun. And it's one of the most beautiful subjects, in my opinion. All right. Thanks for stopping by, Not Prof. My vision has been growing by leaps and bounds. I'm still working on... Okay. Yesterday I got to know something new on Twitter. If you choose a random number between 0 and 1, the number of expected tries you need for the sum of all those random numbers to be greater than 1 is E. Yeah, I think I've seen these kinds of things before. Yeah. E shows up like that. Yeah, I've seen some stuff like that. Yeah, it's always very beautiful when those kinds of expected value problems end up giving E. No, I don't remember the exact argument. There's another one that's more algebraic. It's kind of a riddle, but it's that the number of distinct sets, finite sets in the universe, when you don't overcount them, is E. The number of finite sets in the universe, when not overcounted, you account for overcounting, is E. You should think about that one. Yeah. Okay, look. Look. It's more like a math brain riddle. Okay, look. There's only one singleton set, because each one is isomorphic to every other. And it doesn't have self-automorphisms. So it's just one. Now, there's only one set up to counting multiple times. There's only one set that has two elements. However, you don't know whether it's A comma B or B comma A. So it's overcounting if you put it this way or that way. You get like 1/2. And the number of sets counted without factoring out overcounting is this many. So there's E, total sets counted, finite sets counted, accounting for re-scrambling of everything. Totally makes sense. Sure, the empty set, yes. Oh, the empty set, yes, I forgot the empty set. 1. Yes, correct. Good. Yes, Crow, that's E. Close enough. Okay. All right, but now, hey. Okay, yeah. So now I have to actually prepare for my commutative algebra class. All right. So is there anyone out there? Hey, Professor Peter. Oh. Yeah, no. Pandemic. This I found on Ravi's website. And it's actually kind of important because it's, well, it's not important, but the way, the sort of act of taking a set and only counting it by modding out by dividing out by the number of automorphisms, this idea shows up in a lot of parts of math. Especially when you're thinking about weird objects like orbifolds or stacks. So it's actually something that a mathematician would... It's a little tongue-in-cheek, but the idea of dividing by automorphism groups is very, very, very ubiquitous. So it's less tongue-in-cheek than it seems, but it's obviously silly. Okay. All right. So, hey, Professor Peter, you're here. Did you know that? You're here. That means you made it just in time. Hey, everyone. Professor Peter, also math person on Twitch. One of the originals, I think. Check him out. Let me check him out. Look at this. I was gonna raid someone, and I typically default to Professor Peter, and they're never on. So let's see. Who could we go to? Is Gath on? But and it's also can't. Okay, NC. NC made it. NC made it in the credits. Good job. Good job. Wow. So wonderful. Oh, Melko. Is Melko on? Okay. Let's go. Let's go to Melko. Let's go see the announcement. Oh, got it, Professor Peter. Got it. Okay, let's go. Wait, Melko's not on? All right, let's go there and troll Melko as much as possible.